Have you ever searched something on Google, gotten a route from your GPS, or had Netflix recommend a show you actually liked? All of that is powered by algorithms. Algorithms are the hidden engines behind almost everything computers do. But what exactly is an algorithm, and why is it so important in computer science? Let's start simple. An algorithm is a precise, step-by-step method for solving a problem. Think of it like a recipe. A recipe tells you what ingredients to use, what steps to follow, and in what order. Similarly, an algorithm tells a computer exactly what to do step by step to get from input to output. In computer science, an algorithm has 5 key properties. First, input, it starts with some data. Second, output, it produces a result. Third, definiteness, every step is clearly defined. Fourth, effectiveness, each step can actually be carried out. And fifth, finiteness, it eventually stops. Now, an algorithm is not the same as code. Code is how we write the algorithm in a programming language. But the algorithm itself is the idea, the method, and it can be written in English, pseudocode, or even drawn as a flowchart. Let's walk through a simple example. Suppose you have a list of numbers and you want to find the largest one. Here's an algorithm in plain English. Start by assuming the first number is the biggest, then go through the rest of the list. If you find a number bigger than your current biggest, update it. When you're done, return the biggest. In pseudocode, that looks like this. Set max to the first number. For each remaining number, if it's bigger than max, update max. Return max. That's it. This algorithm has input, the list. It has output, the largest number. Every step is clear. It finishes, and a computer can do it. Now here's something cool. There's often more than one way to solve the same problem. Take sorting a list. You could use bubble sort, which is simple but slow, or merge sort, which is faster, or quick sort, which is fast on average, or Tim sort, which is used in Python and Java. All of these are sorting algorithms, but they differ in performance. Why does that matter? Because performance can make or break a system. A bad algorithm might take hours to process data. A good one might do it in seconds. That's why algorithms are so important. Let's go deeper. There are 7 big reasons why algorithms matter. First, they're the logic behind software. Without a solid algorithm, code is just instructions that don't solve the problem well. Second, they make software scalable. A good algorithm can handle millions of users. A bad one crashes under pressure. Third, they help manage trade-offs. Sometimes you want speed, sometimes you want accuracy. Algorithms help you balance those needs. Fourth, they work hand in hand with data structures. A good algorithm with the wrong data structure can still be slow, but together they make programs efficient. Fifth, algorithms power every area of computer science. Operating systems use scheduling algorithms, networks use routing algorithms, databases use query optimization, AI uses learning algorithms, graphics use rendering algorithms. Everywhere you look, it's algorithms. Sixth, they define what's possible. Some problems can't be solved efficiently. Some can't be solved at all. Algorithms help us understand those limits. Seventh, they shape society. Algorithms decide what you see on social media, who gets a loan, which patients get prioritized. That means correctness and fairness aren't just technical issues, they're ethical ones. So let's go back to our max finding algorithm. It's not just about getting the right answer. It's about getting it fast, using little memory, and being sure it works every time. That's what computer scientists care about, correctness and efficiency. Correctness means the algorithm always gives the right answer. Efficiency means it uses time and memory wisely. We often describe efficiency using big O notation. For example, scanning a list once is O(n). Sorting it with merge sort is O(n log n). Bubble sort is O squared, which gets slow fast. Here's a real-world example. Suppose you want to search a list of 1 million names. A linear search takes up to 1 million steps. A binary search, if the list is sorted, takes about 20 steps. That's the power of a better algorithm. And algorithms don't just matter in theory, they affect your daily life. Google's search algorithm ranks results, Netflix recommendation algorithms suggest shows, GPS uses shortest path algorithms, cryptography uses encryption algorithms, even your phone's camera uses algorithms to enhance photos. And as algorithms take on more responsibility in finance, healthcare, hiring, we need to make sure they're fair, transparent, and accountable. That's why algorithmic bias is such a big issue. If an algorithm is trained on biased data, it can make unfair decisions. That's not just a bug, that's a serious problem. So, what's the big picture? An algorithm is a problem-solving machine. You give it input, it follows a recipe, it gives you output, and it does it reliably and efficiently. Algorithms are the foundation of computer science. They determine what we can do, how fast we can do it, and how safely we can trust it. Learning to design and analyze algorithms is one of the most important skills in tech. So next time you use an app, get a recommendation, or ask your phone a question, remember, there's an algorithm behind it, quietly doing the work.